more specific unit 2 related, i.e. mass spec type question.
Can you repeat the last 20 seconds?
Please, the last 20 seconds.
Yes, what's on the test?
Yeah, what were you talking about?
I'm sorry.
Seriously? All right, you're gonna have a nomenclature question, a synthesis problem, a mechanism problem, a test your reactions problem, and a mass specs page relating mass spec stuff.
Thank you.
Okay. So let's go ahead and pick up where we left off. Okay, so where we left off last time, we were looking at reactions of the aldehydes and ketones. And so I think we were in the middle of doing the reactions of amines. So let's just go ahead and pick up there. Last time, I believe we had talked, what number are we on? So what we had said last time was that the amines are a little bit different because they have different classes of amines. The different class of amine nucleophile that you throw at the carbonyl is going to give you a slightly different product. So what we saw last time was that if you reacted with a primary amine, there's our ketone, and if we say use methylamine, which is a primary amine, the product that you got from this was this type of product, which we called an imine. So that's what we did last time. Let's go ahead and look at what happens if we use a secondary amine. So with the secondary amines, I think I gave you the product already, but we didn't really go through how we got there. So if we were to use, say, diethylamine, this is a secondary amine. The product looks a little bit different. It looks like this. And this is what we call the enamine. So let's go ahead and see if we can find out how we go from start to finish here. Like all of these mechanisms that are acid catalyzed, the first step is going to be having the carbonyl go to grab the proton. Right, so nothing surprising there. And for the most part, this mechanism is going to track fairly closely the mechanism that we did with the primary amine. So the first thing is we protonate the carbonyl. At that point, the nitrogen nucleophile can attack. That generates that tetrahedral intermediate that we keep seeing. And at this point, kind of like what we've done in the previous mechanisms, what I'm going to do is just do a minus H plus step. We need to get kind of to a neutral intermediate before we can really move forward. So we'll lose the proton from the nitrogen, and that's going to generate this neutral intermediate that we saw before. We call that the hemiaminal. All right, so one thing to pay attention to, you'll notice that in the product, that enamine product, you don't have the oxygen present anymore. All right, so what that means is, obviously we have to lose the oxygen. Well, anytime you're trying to get rid of an oxygen, it's almost always done in the same way. We have to make it a good leaving group, And what that generally means is protonated, right? So at this point, it would be nice if we could lose that OH group, but again, you're not going to lose OH as hydroxide. So why don't we think about trying to get rid of it by making it a good leaving group simply by protonating the hydroxyl. And again, that shouldn't be too surprising to you because we are under acidic conditions. So there are plenty of protons around. So once we protonate that, we've got a good leaving group. And at this point, we can kind of do one of two things. You can kind of just make it leave, like as an SN1 style, or you can do kind of that assisted leaving that we talked about, where the nitrogen pushes its electrons in and helps to push the water out. It really doesn't make a difference. Product of that would be this. So if you think back, I mean, in order to complete this mechanism, we've got to give nitrogen its lone pair back in order to make it a neutral compound. And the way we handled that in the previous case with the primary amines was you just simply deprotonated the nitrogen. Right? In the primary case, you only had one alkyl group and there was another H here. And so to give nitrogen its lone pair back, all we had to do was take the H off and give nitrogen its lone pair. Well, the problem now is there's no hydrogen on the nitrogen. So we're going to have to deprotonate from somewhere else in order to get nitrogen its lone pair back. And the best place to do that is going to be right there. So some base, probably another molecule of the amine, would come in, grab that proton, which is going to push electrons in there, and then back up onto nitrogen. And so in the end, what you're left with is a neutral enamine product. We can do a little bookkeeping here. We used a proton there. We got back a proton there. We used a proton there. And got back the proton there. Right, so it is truly catalytic in acid. All right. Any questions on this mechanism? Okay, so we're not going to do a lot with enamines at this stage. We will revisit them in Unit 4. It turns out that they are very, very useful in terms of carbon-carbon bond forming, but we will save that for another time. Okay? All you need to be aware of is how they're formed.
Professor, is the intermediate also hemi or?
Yeah, so this right here would be considered a hemi-aminal. Okay, any other questions on the reaction with the secondary amines? All right, then let's go ahead and keep moving and we can look at the tertiary. I think these are going to be your favorite. So with a tertiary amine, let's start with the same starting material. So this is just going to have, so let me just do methyl, trimethylamine, a little easier. All right, so what we're going to do here is the same thing we've done in all the previous examples. You've got a carbonyl, you're using acid catalyst, and so the first thing that would happen is we would protonate to make a good electrophile. And at that point, the nitrogen nucleophile can add in. And we get to that tetrahedral intermediate. And at this point, what we did in all the previous examples was we deprotonated to make that hemiaminal intermediate. But you may notice, with the tertiary amine, there is no proton to lose. So at this point, there's not really a whole lot you can do. There is no way of really progressing through this mechanism to ultimately lose the water. You might say, well, let's just push on anyway. What we did normally after we deprotonated and made the neutral hemiaminal intermediate was we protonated the hydroxyl to make it a good leaving group. So you might say, well, let's just keep going. So you could theoretically. That's getting kind of weird. You might say, well, let's keep going even further. What we did once we made the good leaving group was we made it leave. So, kick out the water. How are you liking this mechanism so far? Do you like this? How about this? These structures are getting quite ludicrous, right? Having these, anytime you have a double charge of the same thing, like two negatives or two positives, it's not going to be a great intermediate, and especially when you have the same charges right adjacent to one another. I've never seen that in my life. So I would recommend, I don't know if it can exist, like I said, I've never seen it, but I would not suggest including it in your mechanisms, all right? It's usually a bad sign. So the point is, once this occurs, you're pretty much stuck. There's no way you can push this in a forward direction because there's no way to resolve the charge on nitrogen. And so none of this happens, right? All of this is just too much. So the point is, when you try to react aldehydes and ketones with tertiary amines, you get no reaction. Okay? So with the primary amines, we see we get the imine as product. With secondary amines, we get the enamine as product. And with the tertiary amines, we get nothing. All right? Any questions on the amine chemistry?
So we can't have them because the nitrogen can't have a leaving group, or?
Yeah, well, just because there's no way to get nitrogen its lone pair of electrons back. And so if you were to try to continue on with this mechanism, you end up getting into those really ugly intermediates like we just saw with the double positive charges, which just can't exist. All right. Any other questions on this one?
Maybe just, so for the easiest way for the nitrogen to get its electrons back, it's just a top off, right?
Mm-hmm, yeah, exactly.
That's why it is.
Yeah, it would just go back in the reverse direction. All right. Okay, so that is it for amines. So let's move on and look at another one. Many of these reactions will look familiar to you, I think. These are the reductions. So I'm going to start, we're going to talk kind of a few ways of doing this. The first way is the most common way, the one that you know and are very familiar with at this point, and that is the hydride reductions. So these are the really common ones, you know, using LAH, using sodium borohydride. So let's just spend a minute talking about those. We can use LAH, or lithium aluminum hydride. This is something you've been working with for a while now. We know when we take aldehydes and ketones and treat them with LAH, first of all, we have to make sure that we are doing this in an aprotic environment. So it's usually some sort of an ether solvent that's used. But the way we typically view these hydride reagents is just as a nucleophilic source of H-. It is not quite that simple, as we'll see later down the road, but for the moment, we can just consider LAH, and borohydride for that matter, as just H-. And so that's going to behave as any other nucleophile, where it just comes in and attacks straight away. You'll notice we did not need a catalyst here, because H- is a fairly strong nucleophile. And at this stage, we've made the tetrahedral intermediate, and it's just going to hang out until, as with all LAH reductions, we're going to end up protonating, working up an acid that gives the proton to the alkoxide. And we make the alcohol. Okay. So in terms of the borohydride mechanism, it's going to be virtually the same. Okay.
Professor, instead of the ethyl oxide, can we use hydrogen ion?
Instead of the, at which point, sorry?
Is that an ethyl oxide, right?
Oh, no, sorry, this is diethyl ether.
Oh, okay. Can
Yeah.
we use hydronium there?
Hydronium?
Yeah, because I saw it in the reactions. When we were using LAH, we were using.
Yeah, normally the way you see these written is, you know, you have some carbonyl, and you'll see LAH as a step 1 and a step 2 H+.
Yeah.
That's kind of, I just kind of broke those up, right? So here's the H3O plus or H+, same thing, is I just kind of drew it over here, as opposed to all on one arrow, because they are separate steps. You cannot combine LAH in the presence of H3O plus. It would blow up in your face. So, yeah, they have to be done in separate steps. And so this would be the solvent that you ran the reduction part of. So you would actually dissolve LAH in the ether along with the ketone. You would allow that to do its thing, and then once it was over, then you would like throw it in a sep funnel and rinse with acid, just to give this guy its proton. Okay, so then with the sodium borohydride, mechanistically it's going to look pretty much the same. So you have the aldehyde or ketone. We can simplify the mechanism by viewing sodium borohydride as just an H minus. And again, like we just saw, that's going to go in and attack the carbonyl straight away. Now the key difference between these two reductions is while you cannot use LAH in a protic solvent, the borohydride reductions are most commonly done in protic solvents. So as y'all remember from last, what day is it? No, on Monday, when you did your sodium borohydride reduction of the camphor, you dissolved the camphor in methanol. That was your solvent. And the point of that is that if you do these in protic solvents, then the solvent can actually be your proton source. You don't need a second step 2 H plus because the solvent is protic and it provides that proton. But the result is the same. You end up reducing the aldehyde or ketone to the corresponding alcohol. Now, as you can probably tell from the way we've been discussing these two similar reagents, one is much, much stronger than the other, right? So, for instance, in terms of its reactivity, sodium borohydride can only be used to reduce aldehydes and ketones. Okay, so if you have any other carbonyl functional group, like a carboxylic acid or an ester or something like that, borohydride is not going to reduce those. All right?
It won't do anything to an ether, right?
No. None of the hydride reagents are going to reduce ethers. And in fact, that's why LAH is most commonly used in ethereal solvents. LAH, you do have to be careful about using it because it is a sledgehammer of a reducing agent. It will reduce most functional groups. So yes, it will obviously reduce aldehydes and ketones, but it will also reduce carboxylic acids. It'll reduce esters. It'll reduce anhydrides. It'll reduce acid halides. It'll reduce amides. It'll reduce nitriles. Am I missing anything? Probably. But anyway, you can see from this laundry list of functional groups that are reduced by LAH that it is a much, much stronger reducing agent than borohydride. All right. Any questions about these reductions?
I just have a quick question
Mhm.
about the LAH.
Yeah.
So if you when you have the alkoxide step in, what if you didn't use the protic solvent afterwards? What if you use like a bromoalkane? Would that make an ether? Kind of worded that weird. But does he have
Possibly. But that would be kind of a dangerous way to approach it. Yeah. I mean, theoretically, yes, because you have the alkoxide and you could throw in a good leaving group. But nobody would really do it that way. Yeah, it would just be kind of dangerous with all of the LAH remnants kind of hanging out to throw in a really strong electrophile like that. Yeah. So, I mean, in the way you would do that if you wanted to is you would do the reduction, you would then work up an acid, isolate the alcohol, and then take it into like the Williamson ether synthesis. Yeah, and do it in kind of two separate steps. Yeah.
Did you say that the hydrogen that's attacking the carbon of the carbonyl, that's the LAH?
Yeah, that's
Okay.
so LAH provides the H minus.
Okay.
Mhm. And again, that's a bit of an oversimplification, we'll see later, but for now, it's just easier to think of it that way.
Okay, thanks.
Okay, so that is one style of reduction that these aldehydes and ketones can undergo, but it's not the only way that we can reduce them. And yeah.
Is that, so for aldehyde, it's gonna work the same way, right?
Mhm.
Okay.
Yep, the only difference would be instead of getting a secondary alcohol, you get a primary alcohol. All right, so we have seen other ways, other styles of reducing the aldehyde and ketone. So think back to Unit 1, one of the reactions you learned was the Clemmensen reduction. So if you remember, the Clemmensen, what it allowed us to do was take an aldehyde or a ketone and using a zinc mercury amalgam under strong acidic conditions, it reduced the ketone, but not to the alcohol, right? It completely deoxygenated it. It reduced it all the way down to the methylene. So you see how that is a different style of reduction. The hydride reductions will reduce the aldehyde or ketone to an alcohol. These completely reduce it to a methylene. Okay? So it just kind of depends on what you're trying to get as to what type of reagent you're going to use. All right? I want to give you a couple other ways of doing this Clemmensen style reduction. Okay, the reduction of the aldehyde or ketone to a methylene. And so that's what I'm gonna give you two more of these. The third is what's known as the Wolff-Kishner. After the German chemist Ludwig Wolff and Russian chemist, I can't remember his first name, Kishner. He was incidentally a student of Markovnikov. But anyway, the Wolff-Kishner is going to do this for us. Kind of an odd set of reagents, but it combines this amine type structure. By the way, that diamine is called hydrazine. So it combines hydrazine with, under strongly basic conditions, water and high heat, and it will do effectively the same thing that the Clemmensen does. It makes the methylene group. All right. So I want to go through the mechanism of this one with you because it's probably not immediately apparent. But before we go into the mechanism, I'm going to kind of abbreviate it a little bit. Because the first part of this mechanism involves the hydrazine attacking the carbonyl. And we just looked at those. Right? We looked at a bunch of amines attacking carbonyls. So if you're looking at hydrazine, while it's not technically one of the categories of amines, because when we talked about primary, secondary, tertiary amines, I was specifically referring to how many alkyl groups were on the nitrogen. So obviously you don't have alkyl groups on hydrazine, but if you had to put it in a category, what class of amine would hydrazine most be similar to? What kind of an amine does this most resemble?
Primary?
Yeah, exactly. Because, I mean, if you think about it, all we've done is we've replaced one of the three hydrogens that are normally on nitrogen with something else, right? Normally it's an alkyl group, here it's another amine, but still, we've replaced one of the three nitrogen hydrogens. So this is most like a primary amine. So what kind of functionality would we get if we have this kind of primary-like amine attacking the carbonyl? What kind of functional group would we expect? Do we get nothing? Do we get imine? Do we get enamine? Those are really the only three choices.
Amine.
Yep. Just like anytime you react a carbonyl with a primary amine, you would expect to get an imine as a product. The only difference is normally these imines are a carbon-nitrogen double bond with some other alkyl group. Because we're dealing with hydrazine and not a typical primary amine, what's connected to that nitrogen is just the other NH2. Okay? So I don't think we need to go through that mechanism because we did it last time. But this is what the initial product of the interaction between hydrazine and the carbonyl is. All right? So let's go ahead and look at how we get from this imine type structure to the reduced methylene. All right? So the first thing that's going to happen in this one is that strong base is going to come in and grab one of the nitrogen hydrogens, which is going to push those electrons in like this. So if you follow those arrows through, we should have a double bond now between the nitrogens. Still have one hydrogen on the nitrogen. And then the double bond between carbon and nitrogen here breaks, and those electrons end up sitting at that carbon position. So that's going to be the intermediate that we make. And then that is just going to grab a proton from water. So initially, our neutral intermediate is going to look like this. Okay. Any questions on this so far? So we're halfway done. In the next half of the mechanism, things just repeat themselves. Hydroxide is going to come in and grab the other proton, which is going to push the electrons in the same way. So if you follow those arrows, actually this is one of the products that you make here is nitrogen, triple bonded to nitrogen. You see how also this bond is breaking. The carbon to nitrogen bond is breaking. So essentially this N triple bond N is breaking off of the molecule. What is N triple bonded to N, by the way? It's nitrogen gas. you'll notice in this reaction so far, I've drawn all of these initial steps equilibrium. And then I have this massive one direction step. This step is what's known as the driving force of the reaction. It's really what pulls this entire process forward. And that should make sense to you if you think about it a little bit. One of the products that we're making here is a gas. And so kind of by definition, it is coming up out of the reaction mixture. It will bubble up out of the reaction mixture. Well, think about that from a Le Chatelier perspective. If through the formation of a gaseous product, you are continually removing one of the products of the reaction. And as Le Chatelier would predict, if you're continually removing a product, that's going to pull everything in a forward direction. All right? So this is, and we'll see this again a few times, but the formation of a gaseous product is one of the biggest driving forces in equilibrium. All right? So in the last stage of this, we're simply going to grab another proton from water. And so in the end, what you've done is you have completely deoxygenated that carbonyl. You converted it from the ketone into the methylene group. All right. Any questions on that?
Is that gonna work the same way with, just like the first example?
Uh-huh, yep, exactly. So you would just take whatever aldehyde or ketone you have, just throw in those reagents, the hydrazine, OH minus, water, and heat, and out comes the methylene. Okay.
The first one is easier, why can't we just use the first one?
That's a really good question. So why am I torturing you like this? You already have a good way of going from the carbonyl to the methylene group. So why do you need another one to do the exact same thing? Just to make you memorize a bunch of stuff you're never going to use? Maybe. But no, there is a point, right? I mean, look at the different conditions.
What's an example?
One of these uses strongly acidic conditions. This one uses strongly basic conditions. Which one is better? Well, kind of depends on what you're trying to reduce. You know, for instance, if your molecule that you were trying to reduce contained an acetal, you know, you have a ketone that you're trying to reduce, and somewhere else in the molecule you have an acetal, it would be very unwise of you to try to use the Clemmensen reduction, because acetals are easily cleaved under acidic conditions. So if you were trying to keep the acetal in place, you would be much safer to use the Wolff-Kishner. You know, on the other hand, if your molecule had somewhere else in the molecule you had an ester that you were aiming to keep around, well, it would not be a great idea to use something like Wolff-Kishner, because under those strongly basic conditions, your ester would cleave in no time. So it's nice to have, we call these complementary approaches, where you can do the same chemical transformation just under varying sets of conditions. Because some things that you're going to end up working with are going to be base sensitive, and you're not going to want to use Wolff-Kishner. Some things you're going to be working with are going to be acid sensitive, where you wouldn't want to use the Clemmensen conditions. Okay, any other questions about that? Okay, so I'm going to give you one more way of doing the exact same thing. And that is via a thioacetal. So this is going to be something similar to what you've seen before. We talked rather extensively about acetals in the last lecture or two. So what do you think it means whenever we put the prefix thio? What does that indicate? Yeah, sulfur. All right, and that's exactly what it is. So if you think about it, what we did last time was we talked about making acetals. So that was the acetal formation. We talked about that a lot last time. A thioacetal is going to look very, very similar. We're just going to replace oxygens with sulfurs. So, can do very, very similar chemistry here. Now the difference, slight difference, is that because sulfur is more basic than oxygen, right? It's a bigger atom, it's a less electronegative atom, its lone pairs are more available to go and do things like grab protons. Because of that, it's common that we, instead of using a Bronsted-Lowry acid, that could potentially protonate the sulfur, what's more common is to put this on using a Lewis acid. So a lot of times you'll see something like boron trifluoride or zinc chloride or some kind of a Lewis acid rather than a Bronsted acid. But the product is the same. You make this type of thing, which is a thioacetal. So in the same way that we talked about the use of acetals as carbonyl protecting groups, we can also use these as carbonyl protecting groups, because you can put them on and you can take them off. Right? The difference is why you might choose to use a thioacetal over an acetal is because these are much more robust. They're a much more robust protecting group. What I mean by that is, first off, think about how you deprotect an acetal. You remember how we talked about doing that? Once you put an acetal on, you want to take it off. How do you take it off? Yeah, water and dilute acid. But yeah, mostly water. Well, think about how often you're adding acid and water to your reactions or your workup. It's pretty common. So you run the risk with the acetals of kind of accidentally taking them off, because it's very common to add dilute acid to your reactions. So the thioacetal is much more robust. You're not going to take the thioacetal off unless you really want to, because in order to remove it, you have to use mercury salts. So because these thioacetals are removed with mercury, you're not going to ever accidentally remove the thioacetal, right? I mean, how often are you adding mercury salts to your reactions? Hopefully not very often. It's not very good for you. So they're a much more robust protecting group. You're not going to get rid of it on accident. Right? The other thing that you can do with these is they reduce. Treating the thioacetal with hydrogenation conditions in a material called rainy nickel, which is just a nickel aluminum alloy, is another way of reducing to the methylene. All right. By the way, this one also has a name. Sometimes you'll see this referred to as the Mozingo reduction. All right. Any questions there? So now we have 3 different ways of doing the same thing. You can completely reduce a carbonyl to the methylene group either through Clemmensen conditions under acidic conditions, under Wolff-Kishner chemistry under basic conditions, or under the Mozingo reduction with reductive conditions. Right. Which one is better? Well, it depends. It depends on what else is in your molecule.
Do these reductions only work with ketones?
Yeah, only, well, aldehydes and ketones.
Okay, so
Yeah.
aldehydes also?
Yeah.
Okay. Even the Clemmensen reduction too? Okay.
Yep. Okay, I'm gonna give you one last way of doing this, and it's kind of roundabout. So I would, under most cases, probably choose one of the other 3. And this is through tosylation. So if you have an aldehyde or a ketone, one of the things you could do is think about reducing with LAH. So as we talked about, that's going to make the alcohol. You could then put a tosylate group on. Do you remember what tosylates are good for? I think you learned this last semester at some point.
Makes a good leaving group?
Yep, exactly. So the tosylate looks like this. Not that you really need to know. The only thing you need to know about the tosylate is that it's a good leaving group. So then what we can do is treat with LAH one more time. So the LAH, again, you can think of as just kind of H minus. It's just going to come in and act as a nucleophile, kick out the tosylate leaving group. And that gets rid of the carbonyl, just like the other 3 methods. All right.
Do we have to go through all of those, or?
Yeah, if you're trying to do it through tosylation, you have to kind of go through this entire process, which is why I said I think I would prefer to use one of the other methods if possible, because this is kind of labor intensive. Okay, so to summarize. So you've kind of seen a lot of different conditions. To summarize, we have the hydride reductions. Those are simply taking aldehydes and ketones and using either LAH or sodium borohydride, and those reduce to the alcohol. Then we have the second style. And these are going to be reduction to the methylene. And we had a handful of ways of doing this. So we talked about first doing the Clemmensen conditions. Or we could use Wolff-Kishner. Or we could make the thioacetal. And hydrogenate it, those conditions of the Mozingo reduction. Or through tosylation. And all of those give you that.
If you use an aldehyde, it just gives you a CH3.
Mm-hmm. Yeah, exactly. One other thing, I guess I could have thrown. Thrown that one in for the, it's not technically a hydride reduction, but it gives you the same functional group transformation.
Oh, sorry, which one?
Oh, the, up here, the hydrogenation and Raney nickel. On a normal ketone, it's gonna give you the alcohol. And don't forget that exception to the rule. Little carve out here. If your ketone is benzylic and you use hydrogenation, that gives you the methylene group, right? Remember, those benzylic ketones are rather unique. Okay, any questions on the reductions here?
So, is it impossible to do OH on a benzylic?
You can, you just have to use a different reagent. So you would want to use like a borohydride, for instance.
Okay.
Yeah, it's just the hydrogenation is kind of the weird one with benzylic ketones. All right, any other questions?
So for the one, the thios stuff, do we have to do the first step and then do the second step as the vanillical one?
Uh-huh, yep. Yeah, you first gotta put the thioacetal on, and then you would take it and do the hydrogenation to it.
Okay. And you're saying or LAH, that means instead of the vanillical?
Yeah, so, you can use any of these methods separated by or. So, Clemmensen conditions, that would do the reduction. Wolff-Kishner, that would do the reduction. These two here are kind of a set, they would do the reduction. These three here are a set, they would do the reduction. All right. Any other questions?
What about benzylic aldehydes? What do you know about that?
They follow the same kind of pattern as the benzylic ketones. Okay, so the last thing that we've got to talk about in this chapter, got just about the right amount of time to wrap this chapter up, I think, is one of my favorite reactions, and I think it'll become one of yours too. This is a named reaction, and they call this the Wittig reaction. So it would be hard to overstate how important this reaction is and has been in synthesis. You know, I think I mentioned before, obviously if you're trying to make organic molecules, you have to be able to make carbon-carbon bonds. And that's not a trivial thing to do. It's pretty difficult to make carbon-carbon bonds, as it turns out. And usually whenever you come up with a new way of doing it, you end up winning a Nobel Prize. And this was the case for Professor Wittig. He discovered this reaction, I believe, in the 1930s, 40s. And then he was awarded the Nobel Prize for it in 1978. But it is a very, very powerful reaction, and I would strongly encourage you to get comfortable with it, start using it, because it can be really helpful in maximizing the efficiency of your syntheses. Okay? It can serve to kind of replace Grignard reactions. Not totally. I mean, you're going to want to have them both. But the Vitti reaction is an incredibly powerful reaction. So let's just see how we're going to use it. So at its most general, the way you're going to use this is you take an aldehyde or a ketone, and you add it to an alkyl halide, and in the end, you join them together. You end up joining the two pieces together through an alkene. All right? So that's just the kind of the general lay of the land. Let's see how we can actually use this. So the first thing you're going to do is you're going to take the alkyl halide. So let's say we're trying to, let's just use this, keep it really simple at first. So that's going to be our alkyl halide. What you're going to do with this is you're going to treat it with a rather odd reagent. This is what we call triphenylphosphine. And so the pH is just a abbreviation for just a benzene ring. So this is a phosphorus atom that has 3 benzene rings on it. Okay? So if you think about it, phosphorus, where it is on the periodic table, it's just below nitrogen. It's a group 5 atom. So it has a valence just like nitrogen, meaning it's going to be neutral if it's making 3 bonds and has its lone pair. And so that's what I've drawn here. So you've got the phosphorus, it's got 3 benzene rings on it, and it still has a lone pair. And so what's going to happen is just a simple SN2 reaction. In the first step, the phosphorus is nucleophilic as a result of its lone pair, and it's going to go in and attack the alkyl halide and just kick out the good leaving group. So it looks something like this. And what that will result in now is that. Okay. Oh, plus B or minus. And you'll note that the phosphorus is now positively charged. And it's positively charged because the phosphorus is now making 4 bonds. In the same way that if nitrogen is making 4 bonds, it becomes positively charged. Think like the ammonium ion. Phosphorus is the same valence because it's in the same group. So if phosphorus is making 4 bonds, it's going to be positively charged, just like nitrogen. And so to wrap this first stage up, what we're going to do is treat this with very strong base in butyllithium. And what that's going to do is grab one of those protons next to phosphorus. And that's going to result in something like that. And this has another resonance form that I can draw. The other resonance form being this one. Now, if you're looking at the 2 resonance forms, you might be tempted to say, that this is probably gonna be the more highly contributing one, right? Because you, following the normal rules of resonance structures, uncharged resonance structures are normally more highly contributing or better resonance forms than charged ones. And that's usually true. But look at what this resonance form is indicating. It's indicating you have a pi bond between carbon and phosphorus. When we think about how you form a pi bond, a pi bond comes from the overlap of p atomic orbitals. Right? Anytime you're making a pi bond, it's just overlapping of two p atomic orbitals. And that makes the double and the triple bond. Well, phosphorus is a much, much bigger atom than carbon is. And as a result, there's kind of a mismatch in size between the atomic p orbitals. And as a result, this double bond, this pi bond, does not form very well. And so when we're looking at the two resonance forms, this one is actually the more highly contributing as a result of the poor p atomic orbital overlap. And so that's going to play a role in the next half of the mechanism. So by the way, these kind of weird dipolar structures like this are called ylids. So we're using a phosphorus ylid as our nucleophile. So let's go ahead and add this to, we'll do benzaldehyde. So the aldehyde here is going to behave like the aldehyde has all chapter long, meaning it's going to act as an electrophile and some nucleophile is going to attack it. It just so happens that our nucleophile is just a little bit weird, right? A little bit unusual in this phosphorus ylid. But if you look at the ylid, you can see where the nucleophilic site is. Right? The most nucleophilic site on the ylid, well, it makes sense to be the most electron-rich site, meaning that negative charged carbon. So I'm going to go ahead and redraw that down here. So the way this mechanism is going to proceed is the nucleophilic carbon of the ylid is going to go and attack the carbonyl carbon. And that's going to give me something that looks like this. Maybe I'll color code this just for the sake of clarity. Okay, so what I did was I had the negative charge of the ylid come in and attack the carbonyl. Well, there's the O- that resulted as the carbonyl bond broke. Here in blue is the phosphorus ylid that did the attack. What you'll note now is you have a negative charge on the oxygen very close to the positive charge on the phosphorus. Well, opposite charges attract. And so what we're going to do at this stage is form a bond between oxygen and phosphorus. So we make this thing. And then the driving force of this whole process is the formation of a phosphorus-oxygen double bond. Phosphorus-oxygen double bonds are very, very strong. And so enthalpically, they release a lot of energy upon formation. And the way we're gonna do that is bring the electrons down from here, which is gonna break this bond, like so. At the end of all of this, we end up with, number one, the triphenylphosphine oxide. That's the compound that has the phosphorus-oxygen double bond. But more importantly, what we care about is we have brought the two pieces, the alkyl halide that I showed, that I'm showing in blue, and the carbonyl, which I'm showing in black, we're joining them together through the double bond. And this is a very, very powerful way of starting to construct molecules, kind of bringing together, because you can use this for very large pieces, and it has been used for very, very large pieces. You can bring them together through a double bond. Mm-hmm.
Second color the gas?
It is not, actually. It's actually kind of a pain to get rid of. But yeah, it's a solid. Any questions on this reaction mechanism? Mm-hmm.
I'm just a little confused as to why, you said the triphenylphosphine,
Mm-hmm.
why that doesn't have a charge on the end there with the oxygen?
Oh, right here?
Yeah.
Because, well, number one, let me actually
Has to
draw.
do with like the octet expansion?
Yeah, exactly. So, yeah, you'll note, first off, that this phosphorus has a whole lot of bonds. But that's okay, because remember, once you get to a certain level on the periodic table, these atoms can expand their octets. And most commonly in organic chemistry, we see that with phosphorus and sulfur. But phosphorus is always going to be neutral when it's either making 3 bonds or when it's making 5 bonds. So if you go through and kind of calculate the formal charge here of the phosphorus, you'll see that it ends up as a 0 formal charge.
Would there be another amount here or no?
Nope. That's it. Because it's making, if you count kind of, if you assume that all of the electrons are kind of halved, all of these electron pairs are halved that kind of belong to, yeah, well, let me say it another way. If you calculate the formal charge on this phosphorus, it would be, it normally has a valence electrons of 5, and so 5 minus half of the bonding electrons would be 5 minus half of 10. 5 minus 5 is 0, so that's why this is a 0 charge. Okay. Daniel, your question?
Yeah, I wanted to know, why in the slide notes there's no N in front of the, what is it, butyl lithium? And you said that, put an N there?
Oh, yeah, it's just, you'll see it written different ways. It's
Same
the
thing?
N, yeah, it's the same thing. It's just that a lot of people will write N-butyl just to indicate specifically that it's just a straight chain.
But we should just assume they're the same thing.
Yeah, totally.
Okay. And then the other question I have is, if we're using this reaction in our synthesis, do we just, how do we write it out? Like, I mean, obviously we're not gonna do all these steps,
Yeah,
so.
right. So that's what we'll look at a couple examples right now of that.
Okay.
So let's say, if we wanted to use this to,
Professor, is that only gonna work for primary aldehyde?
it actually works for secondary too. It's not as good, it's not as fast of a reaction, but you can use it with secondary halides.
Okay.
Yeah. So let's say we wanted to make this. Let's do that instead. So if you're looking at this one, the presence of those two pieces kind of being joined together through that double bond would strongly suggest Wittig chemistry. Right? And so if you're going to use Wittig chemistry, one side has to be the halide and the other side has to be the carbonyl. So in a case like this, it probably doesn't make too much of a difference. You know, you could envision doing it this way. Or switching them. Either one of those should give us the product we're trying to make, because again, all that's going to happen is the carbonyl carbon, what was the carbonyl carbon anyway, is going to be joined together to the carbon that had the halide through a double bond. I think if it were me, I think I would probably choose this one. It's because remember, you are dealing with SN2 chemistry. The first step is the triphenylphosphine attacking the alkyl halide. And I think SN2 chemistry is going to work better on this as an alkyl halide than on this as an alkyl halide. Okay. But either one would work. And the way you would write this out, if you're going to try to incorporate it into a synthesis, very, very simply. All you have to do is say, just like that. Put the halide plus the carbonyl over the arrow, PPH3 and butyl lithium. Any questions on this example?
So this is just a step faster than like doing yours and then triple outside.
Yeah, it's just a little bit different. You know, it's certainly not nearly as vigorous conditions as a Grignard is. And also it kind of, it brings the two pieces together with a double bond, which can oftentimes be quite useful. You know, because once you have that alkene there, there's all sorts of things you could then do to derivatize that double bond. Or if you just wanted to bring them together, you know, bring these two pieces together, and you didn't want the double bond, you can easily get rid of it, right? Just hydrogenate it out, and then it's just like a big alkene.
Also, the pH is a phenyl group, right?
Mm-hmm.
Okay.
Yep. Danielle, did you have a question? Okay. Let's go ahead. I think we have time to look at one more example. What if I were to give you this one? so how do we wanna do this? I mean, if you're looking at it, we got 2 double bonds in the molecule. So theoretically, we could break this up in a couple of different ways. You know, we could try to do the Wittig reaction to incorporate or to synthesize this double bond, or we could do the Wittig to try to synthesize that double bond. Which one do you think is gonna be easier to do? Do you wanna try to do the Wittig to make the double bond number 1 or double bond number 2?
Maybe 2, I'm thinking maybe because 1, if you do 2, you still have like the benzoic carbon interactide.
Well, let's take a look at our options. Maybe that'll spark an idea. So if we're gonna try to make double bond number 2, what we would need are these 2 pieces. Or vice versa. Put the aldehyde here and you do bromomethane or something right here. Or to make double bond number 1, what about now? Which one looks easier to you? If you had to do this on a synthesis problem on an exam or something like that, which route would you take?
I like the first one.
I would take the second one because it's easier when the pieces are smaller.
Either take this one?
No, the first.
Oh, this,
Number
okay.
1.
Okay.
Number 1, the second
Oh,
option.
yeah, I know, I'm kind of organize that in a strange way, but, okay. Is that you too, Hannah?
Yeah.
Yeah, I would agree. I would take this all day, every day over that one, because that, to me, is gonna be not trivial to make. I mean, you could probably do it, but it's gonna be a whole lot easier to make these 2 pieces than those 2 pieces. Well, I mean, this one you could just start with, but yeah, these 2 are gonna be a lot easier to make than that, I think, anyway. And so that's why I would choose, I mean, both of them would work. You know, it's not a matter of would the Wittig work better here or there, both of them would work in terms of doing the reaction. But in terms of doing the synthesis, I think I would take this one. All right. Any questions on that? Okay, so I would, as you start approaching your synthesis homework, that's gonna be due on Tuesday next week, sorry, Monday next week. I would encourage you to start trying to think about ways of incorporating both the ring opening of the epoxides and the Wittig reaction. Because I think on most of those, I use either one of the 2. Okay, not saying that that's the only way to do them, but on most of those problems, as you'll see on the key, I think I did either through the ring opening of the epoxide or Wittig chemistry. Okay? So again, just start trying to incorporate these into your syntheses. They're very powerful. They can really increase the efficiency of your syntheses. Okay? And then the last thing I wanted to mention is I just passed out to you just kind of a mechanism practice. So it's not due, I'm not gonna pick it up or anything like that or grade it, but it's just, mechanisms tend to be one of the things that give people the most problems on exams. And so, you know, the more practice you get, the better you'll be. So you can do what you will with that, try to work your way through them, or,
Is there a key?
I'll have to look into that. If not, I can put one up. Okay, any other questions? Yeah.
So just to clarify, in this unit for the aldehydes and ketones, we haven't learned any reagents that solely work on aldehydes or solely work on ketones, right? It's always the both of them?
Yeah, yeah,
Okay.
exactly. Yeah, they have very, very similar reactivities. The only thing that really differentiates them is kind of what we talked about at the very beginning of the chapter. Aldehydes are slightly more reactive, but they'll pretty much do all the same stuff, which is why we always kind of pair them together. Okay, I think that's probably a good place to stop. So I will see you in about 10 minutes. We're in the lab. Oh, the ring openings of the epoxide.